catch up with work or whatever it is that you want to do. But I'm not going to be here. I'm trying to organize a trip to Montreal to visit my friend Arshad, but we'll see if that happens. So, while you're on that discussion question, I'm going to do the ye old ladder slipping question. Oh, and this is the other thing, is it's good to sit in the same place every week so that you kind of see the same people. But if you want, balcony people, you can always come on down here, unless you like the air up there. It's all good. A uniform ladder leans against a frictionless wall as shown. So it's a frictionless wall, but it's a friction-y floor. Because if it was a frictionless floor, I think the whole thing would slip out to the right. So how does that work? Well, what is the minimum coefficient of static friction between the floor and the ladder to prevent it from slipping? So, I'm going to try to find, let's use blue, I guess. U sub S is question mark. That's what we're looking for. So what I'm going to do, I'll sort of define the rotation axis right there. This will be the axis. I can define plus y is up, plus x is to the right. And what I want to do to solve this is set the torques equal to 0, the sum of all the forces in the y direction equals 0, and the sum of all the forces in the x direction equals 0. So it's a static equilibrium problem. Those are the three equations you tend to use. It's the same two that we had before for equilibrium situations in which an object's not accelerating. The sum of all the x components of forces is 0, and the sum of all the y components of forces is 0. But now there's a third equation, which is that the sum of all the torques around some rotation axis is 0. So we'll say the system here is the ladder. So we're going to consider forces acting on the ladder and draw them out. And we'll choose, since it's not rotating, you're allowed to choose the axis wherever you want. We'll choose the axis to be the foot of the ladder. So, you got to draw this now extended force diagram. So I will draw the ladder, kind of like that. And now, I want to draw all the forces that I think are acting on it. So, I guess there's gravity, which would be, since it's a uniform ladder, uniform means that I guess the center of mass is at the geometric center of it, because it all has the same density. So that would be mg. So what other forces are acting on it? Well, I guess there's the floor acting up with a normal force, but there's also a normal force coming from the wall, which is horizontal. So there's two normal forces here. So to distinguish them, I'm going to call this one N1 and this one N2. N1 is the sideways normal force from the wall that it's leaning against, and N2 is the upward normal force from the floor that it's sitting on. And then there's static friction. So I think it's going to slip to the right, or it wants to slip to the right. So I'm going to write F sub S going to the left. But there's no friction from the wall. So I think that's all the forces that are on it. So what I'm going to do, remember I told you about the lever arm? So let's just also write a thing, which is that if it's just about to slip, then we do have an equation for static friction. That implies that Fs equals Fs max. And that equals mu sub s times n. But which n? Just the N2, I think, this matters here, right? Doesn't matter what N1 is for the static friction, so N2. It's on the floor there. So the sum of all the torques equals 0. So the way that's going to look is I'm going to have the torque N1 plus the torque of gravity plus the torque of N2 plus the torque of friction equals 0. So I have to figure all these thingies out. So for N1, if this is the rotation axis, then what I can do is kind of find the D1 as being this distance, which is given, actually. D1 equals 2 meters. This is the lever arm for the tau N1. And it's going to try to rotate it clockwise, so that means it's a negative. So this is negative N1D1. Okay, and then gravity, that also has its little lever arm. You just go through the force line and get this distance. We'll call that distance dg. And that's going to be equal to 1.5 meters divided by 2. So that's going to be a, let's see, it's counterclockwise because it pulls down, plus mg dg. And then the normal force of 2 is N2 times 0, since it's acting at the rotation axis. And then the static friction force is also acting at the rotation axis. So those both equal 0. So we don't have to worry about those ones. So now we can simplify that equation, and we can write down that N1 times D1 is equal to mg times dg. And I'll call that equation 1. Because that's not going to help, that's not going to fully solve this problem. We also have to use some of the other equations, such as the sum of the forces in the y direction is equal to 0. So that's going to be, what's in the y direction? There's only two forces in the y direction. There's negative mg, and there's plus n2 equals 0. So that means that n2 is equal to m times g. Those are the only two vertical forces. So we'll call that equation 2. Also, we know that the sum of the forces in the x direction is equal to 0. So there's N1 is acting to the right, and the static friction is acting to the left. That's it. So that means that N1 equals the static friction force. So that's sort of the third equation. So again, these three conditions for static equilibrium give you three equations, and you can solve for up to three unknowns. And there's a fourth equation that we had from before, which is that this Fs equals mu sub s times n2. But we can try to solve this. Let's combine equation 1 and equation 3. And we would get, basically I'm going to plug N1 into there. So I've got Fs times d1 equals mg times dg. And then we can use, again, that fourth equation, use that Fs equals Fs max, which is mu sub s times n2. That implies that mu sub s times n2 times d1 equals mg times dg. And now let's use our last equation, combine with equation 2. We got mu sub s times m times g times d1 equals m times g times dg. Whoops, g. And now there's some thingies that cancel. Divide both sides by m. Divide both sides by g. And you get that mu sub s equals dg divided by d1. So it's 1.5 over 2 divided by 2 meters. It's 1.5 meters divided by 4 meters. And I got mu sub s equals 0.375. And it has no units. That's good, because it's a coefficient of static friction. This is like the minimum. It can also be more than that, and it'll also be in static equilibrium. But that's any less than that, and the whole thing will slip. Okay. Any thoughts on that, or looking okay? And don't be shy about grape candy. I'll just sort of put it here for now. Okay, so there was a pre-class quiz where we were just asked what are the conditions for static equilibrium. It's the sum of the horizontal components as well as the vertical components of the forces acting on the object is 0. Those are two equations. And the third one is that the sum of the clockwise and counterclockwise torques also gets to be 0. If you count the clockwise as negative, I guess, and counterclockwise as positive. Someone asked if I would be able to go through these examples more slowly. I tend to get this comment sometimes on course evaluations. I also get, I wish you would go through things more quickly, which is sort of the opposite. But watch this. This is the great thing, actually, about if you have posted class videos, right? If this comes up.
To the left of the nut.
Yeah, it doesn't. The audio, I guess, doesn't come through. Right?
So it's when people walk.
Anyway, you can click on speed and go to click normal. And click any speed you want. You can make me go faster or make me go slower, depending on what you want. So that would be a suggestion. Go to those Vimeos.
So
cool little trick. Okay. We talk about center of mass. The equation for center of mass is one that looks hideous, but in reality ends up being kind of easy to do mathematically. The real trick that every student misses, and you've got to remember, is you have to define your origin, your axis. First step is define your coordinate system. Where is your origin? Where is plus y, x? Where is plus y? After that, then you can apply this equation. Okay. And you have to set it, right? So, and it doesn't matter where you set it. Once you've set your coordinate system, you'll get the right answer. So we'll practice doing that a little bit. Calculating center of mass is much like calculating your GPA. Marks in a full course, I don't know if you have any of those, the Y1Y courses count twice as much as marks in half courses. So same for this. Particles of higher mass will kind of count for more in a center of mass calculation. It pulls the center of mass closer to the more massive particles. So let's close this discussion question. I'm totally going to read these. Somebody plays trumpet. Someone's very interesting. Somebody has a nice scarf. Okay. Someone looks really sleepy, probably struggling with midterms. Okay. A squirrel crawled on top of somebody today? Holy smokes. Okay. Awesome. Let's do an actual question. Looks like this. Two objects of masses 6 and 8 kilograms are hung from the ends of a stick that is 70 centimeters long and has marks every 10 centimeters as shown above. Does that make sense? 1, 2, 3, 4, 5, 6, 7. Yeah, so 70. If the mass of the stick is negligible, at which of the points indicated should a cord be attached to be right above the center of mass of the system? And what that'll do is that the gravitational torque will be 0 around the point where the cord is attached, and then it won't rotate. So that's the reason you attach it there. See if you can figure that one out. See how I did it. Does anybody want to tell me what the first step to solving these things is? Right, so set your coordinate system, right? So awesome. Define your coordinates. So it doesn't matter where you do it actually, you'll get the right answer. I don't think there's a best place, but maybe, how about I'll put x equals 0 at the left end. And again, doesn't matter where you choose it, but you have to choose it or you can't use the equation. Okay. Back to business. Survey says C. What did I say? Oh, good. But yeah, basic idea. You just now that you've first set your coordinate system, then you've written down the equation, you just plug in the numbers. Let's call this one 1 and this one 2. So it's M1 is 6 kilograms multiplied times X1, which is 0, plus M2, which is 8 kilograms, multiplied times X2, which is 0.7 meters, divided by 6 kilograms plus 8 kilograms. So what you get is 8 times 0.7 divided by 6 plus 8. And I get 0.4. And the units, I think all the kilograms cancel. This is kg. So the units is whatever units you had for the distance. This is meters. Is everybody good with that? Kilograms cancels kilograms, and you get just meters. So that's how that equation works. You see, it's kind of surprisingly simple. And we can do a couple of little demos. One is just this, an unconstrained object, so one that's not on an axle or a pivot, on which there is no net force, will rotate around the center of mass, maybe out in space or something like that. Here on Earth, what can happen is that if you have a center of mass of something like a hammer, it'll balance under the center of mass, and then if you throw it, it sort of spins around that center of mass point. So the center of mass point traces out like a little parabola. And again, we got to work on a video for that or something. But you want to see this aux video, or aux plate, or whatever it's called? Want to see another weird video? So here's a demo that Jonathan brought, which is basically it's just a track, a metal track, and you release something and it rolls down. Okay, so that's right. And then if you put this one on it, it rolls up the hill. So why is that? Why does that one go that way and that one go that way? This one starts at the top, rolls down. So the idea is, what he has done is he has actually tilted the rails so that, I don't know if you can see, if this goes to this side of it, it's actually going up because the rails are closer together here and it's pushing the center of mass of this thing up. So the center of mass of this thing wants to roll to go lower, and it's lower over here a bit than it is over here. Whereas obviously if you have this one, just so it's like pretty cool. Like, can you see it sort of going down? Wants to seek its lowest point. All right, so center of mass wants to try to get down and lose gravitational potential energy as it goes closer to the center of the Earth. Awesome, thank you, Jonathan. Very cool. You got so many great toys over there in your storerooms. Okay. So, when calculating the torque due to gravity, you may treat the object as if all its mass were concentrated at the center of mass. That's sort of the reason why we find that thing. And the reason you can balance stuff is that when an object is in static equilibrium, the torques produced by gravity of the parts. So if you think of this knife, for example, you've got, you can split it into 2 points, or 2 parts, M2 and M1. Well, the handle is more massive, this is M1G, than the knife part because it's much thinner. So M2G is less. But if you put the rotation axis here, this distance x2 is greater than this distance x1. And so the torques are equal and opposite, even though the masses are not the same. So there's more mass on the left side. More mass on the left. The handle's more massive than the blade for this reason, which is that the sum of the torques equal to 0. It's going to be, M1 will be counterclockwise, so plus M1G times X1, and then the blade will be clockwise, so minus M2 times G times X2. So basically M1X1 equals M2X2. If you solve that out, M1 over M2 equals X2 over X1. So X2 is greater than X1 implies that M1 is greater than M2. Handle's heavier. Does that make sense? So it's not the same amount of mass on both sides of the center of mass. If you have different sort of linear densities or something. Okay, let's do another top hat question. drill here. Two objects of masses m and 2m are hanging from opposite ends of a uniform horizontal beam. The beam is being supported by a string at its center, and the objects are balanced. Which must be, the following must be true? So I think what is going on here, let's try to draw it. Uniform beam, and there's a string. It's a bit hard for me to picture. So there's two objects being hung from it. One is here, and the other is some different distance. So they're opposite ends, but they're not necessarily the same distance from the center, if that makes sense. They're not maybe at the ends, opposite sides. So think about that. Check your neighbor and click in, please. Are we good? How much time I got here? Nope. Hopefully you guys saw the timer expire there. Sorry about that. Oh, you got 94% anyway, so that's good. Of the 225 of you that answered, I liked it. The object of mass m is twice the distance. So this is the same sort of thing as the handle. The more massive object is closer to the center. So I don't know how you want to do this. You could call this M1G and X1 and M2G and X2. So it's just sum of the torques equals 0. So M1G times X1 minus M2G times X2 equals 0. G's cancel. You get basically X1 over X2 equals M2 over X1, M1. 2M over M. X2. So I like C. So sometimes people ask me physics questions on this little pre-class survey thing, which is, it was meant to be part of the pre-class quiz every morning, but I found out if I put an essay question in the pre-class quiz on Quarkus, it refuses to mark it until I go through and manually mark every one. But anyways, someone asked this. A uniform meter stick with a 50-gram object on it is positioned as shown below. The stick extends 30 centimeters over the edge of the table. If you push the stick so that it extends slightly farther over the edge, it tips over. Use this result to determine the mass of the meter stick. So you define the system to be the stick, S. M1 is the little mass over here that's sitting at the end, if you can see it. That's the 50-gram object. M1 equals 50 grams. And then, so I think if you define the system to be the stick, there's three forces acting on it. There's going to be the force of gravity of the Earth acting down, like Fg or something like that. There's going to be, and that'll be, if it's a uniform meter stick, it'll act at the 50 centimeter mark. Then there will be the upward normal force from the table, and then there will be the downward force of this object on this end. It's actually a normal force, but it'll be equal to m1 times g, because you've balanced the m1g, so it's got an upward normal force on it. So by Newton's third law, it'll push down on the meter stick with a equal and opposite force of m1 times g. So when you solve this problem, you don't do the normal force. So I'll show you how you solve this problem. It's a bit strange. What you do, so there it is again, is you draw an extended force diagram of the meter stick So there's the meter stick. And what you do is you place the table under so that it's only touching at the right edge of the table. This is the whole trick. So, what you do here is, I will just put it down here, just about to tip means that only the right edge of the table is really touching the meter stick. So all of the normal force gets exerted by the right edge of the table, if you can kind of imagine that. Otherwise, there's no way to solve this problem. Because you have to draw the normal force somewhere on there, right? Right edge of the table pushes up on the meter stick. And then what you do is you just define the rotation axis to be there. Define the axis to be the right edge of the table. So this is the table, and this is the stick. So what you've got, let's draw the forces in red here. You've got, we know that this one is the gravity, m times g or something. And we know that this is going to be the pushing force from the little mass. So I'm going to put all the normal force right here. And I'm going to define the rotation axis to be right there as well. Axis. So that when I do, my sum of my torques is equal to 0, and I've got the torque of gravity plus the torque from the table plus the torque from M1. It's going to be 0 is equal to, this one's pulling in the counterclockwise direction, so that'll be a plus capital M times G times, let's call these distances, we'll call this one D2, we'll call this one D1. I think D2 is going to be probably 20 centimeters, right? And D1 is going to be 30 centimeters. So, and then plus the normal force times 0. That's the answer to the student's question. I've just defined the rotation axis to be where I think the table's pushing up on it. And then minus M1 times G times D1. So you get M times G times D2 equals M1 times G times D1. The G's cancel. You can divide both sides by G. And you get that capital M is equal to M1 times D2 divided by D1. So it's the 50 grams times the 30 centimeters divided by the 20 centimeters. So I'm going to be lazy and not even convert to SI units because the centimeters will cancel. And I'll get M is equal to 75 grams. It's the mass of the meter stick. Oh my goodness. Go a little slow. Okay. That's okay. Yes. Yes, question?
How did you know that the gravity working on the ruler was 50 centimeters from the end of the ruler?
Well, that part is this uniform ruler thing. The center of mass of a uniform object is at the geometric center of it. So if a meter stick you know is 100 centimeters long, then 50 centimeters is the center of the meter stick. There's a lot of little tricks like that in this problem. Yep.
It's supposed to be D1 by D2.
Oh. Yeah, I think I got a mistake there, right? Which is okay, because the numbers are right, but the letters are wrong. So let's just correct it in green. Sorry about that. Thank you, thank you. So that's right. This is a D2 on the bottom, and this is a D1. But D1 is 30, and this is 20. Thank you. Mistake in the original thing. Anybody else? There was a hand over here, but was that it? Okay, thank you. All right, this morning's pre-class quiz, let's go over it a little bit. This was the boat thing. I mean, you know, 99% is great, but let's just draw the boat. and give the idea here. Here's the boatman with some mass, and here's the boat. So what you do, first step is define your axes, set your X and Y or something like that. But basically the center of mass of the boat, or the system, boat and man system is going to be the mass of the man times X of the man plus the mass of the boat times X of the boat divided by this sum. So if the person goes to the right, goes up, then the center of mass will go up as well. And then this one, some people were wondering how I got 1.25, so let's, please help yourself. Let's draw this. You've got a 20 kilogram uniform beam. So we can write it down somewhere. The mass of the beam is equal to 20 kilograms. And it's 10 meters long. How far from the man is the center? So let's put a man here standing at one end. The mass of the man is equal to, so there's M, is equal to 60 kilograms. So how far from the man is the center of mass of the board system? So there's going to be somewhere here will be the X center of mass, right? What's the first step? Center zero, exactly. So I can do it wherever I want. Someone pointed out that you will get a different numerical answer depending on where you set your zero, but it'll always be in the same physical place. You could check it by trying different 0 points, but I like to put it where something is, so let's put it right over here where the man is. Let's set X equals 0 right there. And then this is the X direction there. So what you get is X center of mass, which is what you want. This will now give you the distance right away. So you know the drill. xm times mm plus xb times mb divided by mm plus mb. So it's equal to 0 times 60 plus, what's xb? I think it's going to be the center, yeah. So what's that number? What do I use here? Somebody yell a number at me. We want to yell a number? 5. I like that number. Times 20. And then you divide by 60 plus 8 plus 20. So it's equal to this. The 0 doesn't, so you go 5 times 20 divided by 60 plus 20. Anyway, you work that out, and you get 1.25. And so this was in kilograms, and this was in kilograms. The kilograms canceled, so you use the same units as the 5. So it's 1.25 meters. Okay? Okay. So in equilibrium, an object has no net force, no net torque. I'm kind of going over this stuff a few times here. You draw an extended force diagram, you set up your X and Y axes, you choose a rotation axis. All of these choices, I guess, should be done to simplify your calculations, but they don't have to be. Each force has an X and a Y component, sum all these up, and there's the equations. Let's do another example. This is a term test-like question. A uniform meter stick, again, so you know its center is going to be there. Length 1 meter, obviously, has a 0.2 kilogram mass suspended by a string from its left side. And it rests on a pivot that is L over 3 from the left side, so 33.3 centimeters or something. If the system consisting of the meter stick and the hanging mass is in equilibrium, what is the mass of the meter stick? So again, we've done this, but let's see if we can just do it with torques. You're going to say, what's our first step here? I guess what I'll do is set this x equal to be 0 over here. Actually, no, wrong. That's not what I wanted to do. I think it's easier if I set the x equals 0 to be at the pivot point. So let's set this to be x equals 0. And so this will be, there'll be a L over 3 and there'll be a 2L over 3 on this side. Well, wrong. That's to this edge. So I guess the question is, how far is this? I think this will be L over 6 from here to here. So what you get is you get M1 times G times L over 3, and then minus the mass of the meter stick times G times L over 6. Whoop. Very sloppy today. Equals 0. So sort of like 0.2 L over 3 equals mass of the meter stick times L over 6. 100 centimeters cancels out both sides. And you get the mass of the meter stick equals 6 divided by 3 times 0.2 kilograms. And you get 0.4 kilograms, which is E. And what do we have time for? Okay. So the next two questions, well, the next question, which I'm going to give twice, is from a problem set, which is now on there, which is you've got this diving board. So this is questions 3 and 4, I think, from this problem set 7, I think, one where you have to write out an answer. A man is standing on a diving board. The board is fixed in 2 points, point 1 and point 2, or posts or something. So they're called posts, they're called piers and something, but basically they might be glued to the board. So ordinarily, normal force only pushes away from a surface. But you can imagine if something is sticky and glued to it, you could have a perpendicular force to the surface which is pulling as well. So I'm not ruling that out here. Okay? Which of the following is true about F1 and F2? The forces exerted by the posts at points 1 and 2 of the board. So is it F1 is pushing up, F2 is pulling down? Both F1 and 2 are pushing upward, as you would expect with normal forces. F1 is pulling downward and F2 is pushing upward. Or it might be a various combination depending on the mass. Check your neighbor and think about the torques here. To balance the torque of the man pushing down on the right end, right? So C, F1 is pulling downward, F2 is pushing up. So the big question here is why. I also liked that. And I ended up doing this twice. I'm trying to see what the difference is. It might be that there's different rotation axes. Let's see what I was trying to do here. So the first way I solved it is I said, let's choose rotation axis equals like 1, the left end. Seems to be a favorite of mine. So if you've got, here's F1 and here's F2. I don't really know ahead of time which directions these forces will be, so I think I'm just going to draw them both to be up, and if one of them comes out to be negative when I do the math, I'll know I drew it in the wrong direction. But I do know, if the system is the board, that this will be pointing down, the mass of the man times G. And there might even be a mass of the board, but I think they said it's negligible. So, so what we've got here is some distance, whoops, x2 is from here to here, and maybe xm is from the whole length of the board from there to there. So the sum of the torques is equal to 0, will be F1 times 0 plus F2 times x2, and that's going to be, the way I've drawn it counterclockwise, it'll be plus, even though it might not be right. And then minus the mass of the man times G times X of the man. And I can, if that equals 0, I can say that F2x2 is equal to the mass of the man times X times M. So, and that'll be, so everything worked out all right. So I think this is going to be greater than 0. So F2 is greater than 0. So that didn't really work, did it? Well, let's do the alternative method. Let's choose. I think what you'd have to do here is balance out now that's the sum of the y forces. So let's choose 2 as the rotation axis. See if this works out a little bit better. And again, here's F1 and here's F2. Now we'll say that, and this is x, we'll call that still x2. And this will now be, I guess, x m2 or something. It's a different coordinate system, so maybe I should call it something else. But the point here is that the sum of all the torques, which is equal to 0, is going to be F1 times x2. That's counterclockwise now. Okay, or sorry, yeah, it's clockwise, so it's negative. And then this is also clockwise, so minus m, the mass, times x, so times g, times x m2. So what I now get is that F1 times x2 is equal to negative m times g times x m2. So this has got to be less than 0. So F1 is less than 0, so it goes down. So depending on where I chose my rotation axis, I get a different force, a fact about a different force. Does that help? So what I got is that F1 is pulling downward and F2 is pushing upward. I got sort of C. And the other thing that you can do once you have numbers for these things is you can check that the sum of all the y forces is equal to 0 as well. And then you don't have to keep choosing different rotation axes. But okay. I had a whole thing I was thinking about doing, which I don't think I will do, because we'll have lots of time when I come back from break. It was going to be just this question about forearm. But one thing I wanted to mention is that tomorrow, this is where I'm going to be at 8 p.m., is Isabel Theater. This is a free event. They ask you if you want to reserve a seat, you can click on this, or you can just show up. But this guy is named Stephen Morris. I don't know if you've ever seen him before. He's a friend of mine, been a professor of physics here for a long, long time. He works on pattern formation in nature. And so he takes all these great, amazing videos of things, and I guess you're helping him, Jonathan's helping him set up a demo. So this is all going to happen tomorrow, and there's a lot of music and movies and things like that by all these musicians. So he's teamed up to do a kind of like physics arts event if you're interested in physics and the arts. Check it out. There's other fun things going on either this weekend or the ago, all this stuff. Try to get some sleep. I'll see you guys in about 10 days or so. So have a great reading week. Bye.